Good morning, everyone. Today, our group, Algo Squad, will be presenting our assignment on structures and strategies of state space search using the 8 puzzle problem as our example. The aim is to understand how different search algorithms explore a state space to reach a goal and to compare uninformed and informed approaches. Let's start with the problem itself. The 8 puzzle is a classic problem in artificial intelligence. It consists of a 3 by 3 grid containing 8 number tiles and one blank tile. The task is to transform a given start configuration into the desired goal configuration by sliding the blank tile up, down, left, or right. For example, here the start state has tiles arranged randomly and the goal state is ordered from 1 to 8 with blank at the end. It is important to note that not all starting positions are solvable. Solvability depends on something called as inversion parity. If two states have different parity, then it's impossible to reach one from the other. The total state space size for the 8 puzzle is 9 factorial by 2, which is 181,440 states. Clearly, we need efficient ways to explore this state space. The puzzle can be formally represented using a 4-tuple NASGD. N is a set of all states or nodes. Each state is a 9-digit tuple representing the puzzle configuration. For example, N1 is 1, 4, 3, 7, 0. 0 represents the blank space, 6, 5, 8, 2. Then there is A, which is a set of transitions or legal moves, where the blank swaps with its neighbor. The legal moves in this case are up, right, down, and left. S is the start state and GD is the goal state. Usually, the goal state is considered as 1 to 8 in a sequence and 0 or blank space at the end. Here, you can look at the state space graph of the 8 puzzle problem. We can move from the state N1 to N2, N3, N4, or N5 by the moves up, left, down, or right, respectively. These moves are the moves of the blank space, which is colored in black here. Coming back to inversion parity. An inversion is a pair of tiles A, B, where A comes before B in the linear representation, but A is larger than B. The blank is ignored when counting. To check solvability, we count all such inversions. If the total number of inversions is even, the state belongs to the even parity group, and if it is odd, it belongs to the odd parity group. For example, here the states n1 and n minus 1 are not reachable from each other because n1 has 10 inversions and n minus 1 has 11 inversions. So they have even and odd parity respectively, hence they are not reachable from each other. Two states are reachable from each other only if they have the same parity.
Uninformed search algorithms. They are basic problem solving methods that don't use any extra knowledge about the domain. They blindly explore all possible states until they find the goal. The main algorithms we'll discuss here are breadth first search, depth first search, and iterative deepening depth first search. Let's start with BFS or breadth first search. Imagine you're solving a puzzle. BFS explores every possible first move, then every possible second move going level wise. It's like searching breadthwise, expanding every option at one depth before going deeper. This guarantees completeness. If a solution exists, BFS will find it. Also, it's optimal for uniform step cost because it always finds the shortest path. But BFS is memory heavy. At depth D, if the branching factor is B, it has to store all B to the power D nodes at that level. This exponential growth causes high memory use. Similarly, BFS time complexity is also order of B to the power D since it expands all nodes up to the depth D. Here the diagram shows the search starting from the initial puzzle state exploring all possible moves at the first level, then the second widening the frontier systematically until the goal is reached. Next is DFS or depth first search. So, unlike BFS, depth first search dives deep down one path as far as possible before backtracking. If it hits a dead end, it returns and tries another path. DFS is memory efficient using only order of b times d space since it only stores the current path and siblings, not the whole level. Its time complexity is also order of b to the power d in the worst case, as it might explore all paths deeply. However, DFS is not complete for infinite or very large search spaces since it might get stuck down going an infinite path and never find the goal. It's also not guaranteed to find the shortest solution as it returns the first goal found on a deep path. The diagram shows DFS moving deeply down a single branch first, then backtracking and trying other branches, resulting in a deep and narrow search pattern. IDFS or Iterative Deepening DFS. IDDFS combines the best of both worlds. It repeatedly runs DFS with increasing depth limits. First depth 0, then 1, then 2 up to D. This gives the BFS completeness and optimality because it eventually explores all nodes at shallow depths before going deeper. At the same time, it maintains DFS low memory use, order of B times D, by searching depth limited paths. Its overall time complexity stays order of b to the power d since most nodes are at the deepest level and are expanded once, while nodes at shallower depths are revisited but don't cause any excessive overhead. Here, the diagram illustrates repeated DFS at increasing depths, showing a layered search that expands wider gradually until the goal is found.
Now let's move on to informed search. In informed search, we use heuristics to guide the process. This makes the algorithm faster and more practical for larger problems. We'll be focusing on A star and hill climbing algorithms in informed search. The first algorithm that we are using is the A star algorithm. A star algorithm expands the most promising node chosen according to the evaluation function f of n. Evaluation function f of n is a combination of two other functions, which is g of n and h of n. G of n is the cost from the start to the current node, and h of n is the heuristic estimate from the current node to the goal. For the 8 puzzle, we use Manhattan distance heuristics, which is the total number of steps each tile is away from its goal position. Because Manhattan distance is admissible, never overestimates, and consistent, A star is guaranteed to find an optimal solution. A star is complete and optimal, but its drawback is that it is memory heavy since it stores all the generated states. The space complexity of A star algorithm is O of b raised to d, and the time complexity is the same. The diagram in the slide illustrates how A star expands the most promising node first, efficiently narrowing down the search towards the goal n. Moving on to hill climbing search algorithm. The hill climbing algorithm is a greedy algorithm. It looks only at the neighbors of the current state and moves to one state with the best heuristic value. It is memory light and simple, but it suffers from serious drawbacks. It can get stuck in a local maxima. It can also stall on plateaus or ridges where no better move is visible. In the 8 puzzle, this means hill climbing often fails because sometimes solving requires taking a step that seems worse temporarily. Hence, the completeness is not guaranteed. The time complexity and the space complexity of the hill climbing search is O of b raised to d. Moving on to the runtime of hill climb search algorithm. So we start with the start state, which has a heuristic value of h is equal to 2. Next, we check left, then we check right, then we check the up, and we check the down. The least amount of Manhattan distance is in the down move. And since hill climbing approach is a greedy approach, we'll choose the h is equal to 1, which is the down move. Now, in one of these states, after h is equal to 1, we get the goal state, and that is a solution.